Hi, my name is Emily Wachowski, and today I will be talking about the finite difference form of the heat diffusion equation. This is with no heat generation and constant properties. So since we have constant properties, this alpha equals Kp, or K over rho times Cp, which is the heat diffusivity constant. And then since there's no heat generated, this Q here can be 0. We can disregard that. And then that way we can rewrite it to be alpha times second derivative T. Oops. So that way we can rewrite that. And so since we're doing the finite difference form, we can think about a bar with just split into finite sections. And each section is going to be considered delta x. And then we're also going to have, like with respect to time as this is flowing through this, it's going to have different temperatures throughout this bar. So we can write first we have to simplify the second derivative, and then we also need to rewrite this side of the equation, which first we can think about tjn, which n is going to be an integer for the change in time, and j is going to be an integer for delta x. So it's going to be equal to t, and then n equals, time equals n delta t, x equals j delta x. So then there's that. So first we can start off with this side of the equation, which would be, it's going to be, so for this you won't be changing the position, you're just changing the time because of the denominator. So you're going to do the same position for each of them, but at a different point in time. So you're going to be changing your n. So it's going to be tj n plus 1 minus tj n over delta t for this side of the equation. And so it's still going to be equal to this, but here we can split up the second derivative into this, because we're going to have to approximate the second derivative. And then here, you're going to subtract, you basically do the same thing that you did here, but you're subtracting 2 points in time in order, not 2 points in time, but the different positions in order to approximate the second derivative. So the first delta t over delta x will equal tj plus 1 n minus tjn over delta x. And then the second one, so this right here, would be tjn minus tjn delta x. So this is at a later point in time, and then this is at an earlier point in time. And then you can plug that back in to get equals alpha tj plus 1 n minus tjn over delta x minus tjn minus tjn plus 1 delta x, and then this is all over delta x. So this is basically change in slope over change in x. That's how you're going to approximate the second derivative. And we also know that this is finite because we're using actual x values, and then we're doing actual differences over small differences in either like time or position. And from here, you can set this equal to that part of the equation that I wrote up there, bring that down, and then you want to get tj to the n plus 1 by itself in order to simplify. So here I'll just simplify. You get tj n plus 1 equals tj n plus alpha delta t, because over delta x squared from here. And then you'll end up with tj plus 1n minus 2tjn minus tj minus 1n. And then there is your final answer. So, and let's see, is there anything else I need to explain? I don't think so. So yeah, thank you so much.
Finite differencing that I talked about in the first part of this video, but this time we will be plotting to see how the temperature changes over time with this, and we still are doing the bar, and at the left side of the bar the temperature is 350 Kelvin, the right side is going to be 400 Kelvin, but your initial temperature is 300 degrees Kelvin. So the first thing we're going to have to do is import numpy. This will help us for any like operations we want to do with arrays or anything like that. There's a lot of information that it's importing. And then we also need to import .io as PIO, and then so this is because we are going to have to plot, and from this we're going to need the subplots from this. So okay. And from here we're going to say nx equals 100, which this is going to be the amount of divisions in the bar. So like your change in x, like how many of those we have. And then nt is going to be your timestamp, so it'll be 1,000. This is basically like how many time intervals we're going to have. And then the next step is r equals 0.1. That'll be our first value for r. This is going to be your heat diffusivity constant times delta t over delta x squared, which this is from the first part of the video. But yeah. And then we're going to have our equation for the bar. It's basically just importing the bar into the code. And then our temperature on the left side is going to be 100. It's 350. And then temperature on the right side is going to be 450. So the reason you have to do -1 is because in Python it only goes up to the end value -1, so you can indicate that you're going up to the last value by using -1 instead. And then t equals 0, so the index always starts at 0 for your initial value, so that's how you know that that's the leftmost value for the bar. And then so x equals mp dot. This is basically just importing like your axes equation, and then from here we can make our graph. It's going to be for your initial temperature, and since we only want one graph, we just do rows equals 1 and columns equals 1, and then is, oops. And your axis x equals x because your x is just going to be your change in position, and then your y-axis is going to be your time, and it does like that. And then, or did I just say your time? I meant your temperature. It's going to be your initial temperature. And mode equals lines because we want the dots to all be connected. And then you can name this, oops. Then from here we can use the equation that I derived in the first half. So it'll be, well, first we have to do for I in range. Then we do, oh, I need to do T1, -1, so we can look at the current temperature, and then equals the current temperature, oops, I need to capitalize that. Current temperature times 1, -1, and then plus sign, plus R, no, R times, and it'll be, I keep forgetting my caps lock sign. Like that. 2 times. Let's get current temperature. I'm just going to type this all out first, and then I will talk about it. Trickling. Oh, did I never? I think I messed something up here. Times 2. Oh, I did not need to do that. I meant. Okay. And then plus. Oh, I don't even think I need that. And then I think that's it. Oh, okay. So basically this is going to be your current temperature here. Oh geez. Oh. So I think you can see my cursor. So this is going to be your current temperature, and then this is going to be your temperature to the left, and then your temperature to the right, and this is also your current temperature here. Basically just making sure you are including everything. And then turn my caps lock off. And then so we're gonna want what's the word? Oh, we want to graph for like a certain amount of time intervals. So if I 100 equals 0, so this will allow for every 200th timestamp to create a graph. So fig, and this is making the new temperature. So it'll be the temperature at whatever position you tell it to be at. And then so name equals F I So yeah, so this is going to be like whatever position in time you're at. So then if we do, oops, this, let's get out of that. Let's try to run this. Let's see how that works. Oh. Oh, I spelled it wrong. Now let's try. Oh. Okay. What did I do? Oh. I don't think that's how it's supposed to look. But, okay. I think I just didn't have. Let's change this. Okay, that doesn't do anything. Oh, well, basically you can see here, it doesn't go up to the final temperature. So if you do NT plus 1, I definitely messed something up. Oh, I think that's right. I don't know if that'll make a difference. Oh my gosh. Okay, there we go. So this is what it's supposed to look like. So let me redo it so you can see what it looks like when it's not including the final. So basically you're going to see it doesn't go up to the final temperature. So you add the NT plus 1. There you go. It's crazy. One indent can do that. Just mess up the whole graph. Well, it's not crazy. It's how it works. But anyways. So you can see here that as time goes on, temperature changes. And so this is basically saying, oh gosh, I'm like messed up from having to fix my code. But yeah. You can see as time goes on, the heat diffuses throughout the bar, and then you can, so you won't really ever be able to change your heat diffuse. I can never say it, but you won't be able to really change this constant. But you can change, like you can manipulate your change in time and your change in X. So, okay. So you can see here that when you use R equals 0.55, it creates this sort of oscillation here because whenever R is greater than 1/2, it's unstable, and we will prove why in the next video. But if R is 0.5, you can see here it's still pretty stable and it's coming up off the x-axis more, which is good. It's progressing more. But if it is equal to 0.55, or like you can make it 0.6, and it's just going to keep fluctuating more. So finally, I'll show 0.1 again compared to 0.55. But yeah, back and forth. Yeah. So thank you so much.